Hi class, let's get started. So from today we will discuss the truss analysis. So we'll get started with the method of the joints. So let's do a review of what we have already discussed so far. So by so far, you should be able to solve the problems like if I give you the beam, one side is pin, another side is roller. So you should be able to solve after I give you a geometry. You should be able to solve what's the AX, AY, and the BY. Okay, so by using the three equation of equilibrium we discussed before, which is sum of moment on any point equals to 0, sum of the fx equals to 0, and sum of the fy equals to 0. Okay, so you should be able to solve the resultant from the support very easily. And also for other cases, okay, the force sometimes can be a distributed force. Okay, you should be also be able to convert the distributed force into a single force, okay, into a single loaded force. Okay, that's what we have already done, discussed, learning so far. So, but from today, we'll get started by talking about trusses. So, what's a trusses? I will show you more example later, but by the definition, the trusses is used to support the roofs, crane, bridges, etc. So it's actually anywhere in a structure. And the purpose of the truss analysis. Okay, what's the purpose of the trusses analysis? Is to find the force each member supports. Okay, so we need to find like the force within each members. And by doing this, in your future class, okay, you will be able to select the member size. And here are some assumptions when we are doing the truss analysis. So first, loads, okay, they are applied. And joints. The second, we neglect the member weight. And then each member is a two-force member. And they are bolted at joints. So there are two forces member, which means they are will be either tension or compression for each of the members. And here we can pose a little bit and have a little bit question for you. So which of the members needs extra size in the design? So answer should be for the compression. The compression members is usually designed thicker to a wide buckling. Okay. Here are some examples of the trusses. So actually they're anywhere. They're on the buildings, cranes. So it's almost anywhere. But before that, before we move to for the method of the joints, let's talk a little bit about what's the zero force members, which can save your time for the analysis very heavily. Okay, so type 1, the zero force members is if joint with two non-collinear members and there is no external force on reaction. Okay, and then the both members, they are zero force members. Zero force member means there is no force for this member. And type 2, if the one joint has 3 members, 2 are called linear. No external load or support. Then the third member is zero force member. And when we are doing a trusses analysis, the zero force member can be excluded from the analysis. Okay, so let's see 2 examples of the zero force members for the type 1. So for the joint A and D, they are both the joint with 2 non-collinear members, and there is no external forces or reaction. So both of the members, they are zero force members. Therefore, we can remove those 4 members in the analysis. So after the remove, the truss is much more simplified. For the type 2 and point joint D and C, there are 3 members, okay? And 2 of them, they are collinear, and there is no external loads and supports. And then the third member, which is not collinear with the other 2, it should be 0 members, okay? Let's mark here. After remove the 0 force members, the truss is simplified. Okay. So let's see an example for the truss analysis. So let's first check if there is here the truss. A is a rotor, C is a pin. We have external force acting as a point joint D. So first let's check if there is any 0 force members here. So if we look at the joint B, okay, if we look at joint B, it has 3 members. 2 of the members are collinear, and there is no support and no reaction, external force. which means this member is zero force member. Okay. So which means FBD equals to 0. Okay, without doing any math, without doing any equation, we can know FBD is 0. Okay, so here's our plan. So as we discussed, first we need to check if there is any zero force members, and we need to then first analysis at each joint. So we can get started with the joint D, and then analysis joint A. So for the joint D, because FBD is 0, so for the point D, it has 3 forces. One force is external, the 450 lap, as shown in the blue, and the other two, they are FAD and FAC. They are both in the forces from the members. And then we can apply two of the equilibrium equation. First one is sum of Fx equals to 0, and second one is sum of Fy equals to 0. For this, our assumed positive direction for the x is to the right side. So that's why we have a negative for the 450, and plus FCD times cosine 45, and minus FAD times cosine 45. And for the y direction, I will assume positive direction is upward. So that's why we have negative for both FCD and FAD. So negative FCD times cosine 45 minus FAD times sine 45 equals to 0. After solving these two equations, we can get the answers. FCD is a positive 318 depths, which means the force direction is the same to our assumed direction. And the member FCD, it's in tension. And for the FAD, it's negative, which means FAD is in compression. Okay. And then FAD and FAB, they are already solved. The only thing unknown at point A is AY. So we can use So for the point A, the FAD already solved. We have two unknown, FAB and FAY. We can use the equation sum of Fx equals 0, and we can get equation FAB plus negative, which is FAD times by cosine 45 equals 0. And then we can solve FAB is 225, and FAB is in tension. Okay. So let's see the example here. How many zero forces? So first, at this point, it's a two-member joint. They are not collinear, and there is no external force, so which means those two members, they are both zero force members. And for this joint, it's three members, two of them are collinear, and this member should be 0. So you found, attention quiz 1, you found FBC is negative 500 Newton. The member BC must be in tension or compression. So let's draw the figure. FBC is negative, which means FBC on point B is in this direction, and based on the Newton's third law, we can know the direction on the joint and the force direction on the member should be opposite. So which means FBC on the members this direction, which means the member is in compression. And last, when supporting the same magnitude of force trusses member in compression are generally made thicker, thinner, or the same size when in tension. So the number should be thicker. As we discussed before, if the member is in compression, it should be designed thicker to avoid the buckling. Okay, so that's pretty much for today. Please finish your homework, and I believe you need to do a lot of exercise for this part.